welcome to our third webinar of the fall for the USACM Energy and Earth Systems Technical Thrust Area. Just to say a few words about the Technical Thrust Area for those who aren't familiar and who aren't familiar with our webinar series. We were founded about a year and a half ago. We are part of the U.S. Association for Computational Mechanics. So if you're a part of USACM, you can join for free. You'll get information about things like this webinar series. It's also possible to follow us on LinkedIn for free to get updates on some of our activities. And essentially, we cover a wide range of topics that are listed here, from climate couplings to climate and earth system modeling to geomechanics to different kinds of energy, wind, solar, nuclear, carbon sequestration, capture and storage, oil, gas recovery, and so on. We have this monthly webinar series that takes place on Tuesdays, plus minus. Sometimes we have to do a little bit of a change to accommodate a speaker. So we'll be doing this through May during the academic year, once a month. The webinars are recorded and posted on our TTA site for those who'd like to see them after the fact. We have one more webinar during the fall semester, which is December 17th by Professor Todd Griffith from University of Dallas, Texas at Dallas. He will be speaking on wind energy. He actually said his title, but I didn't have a chance to update the slide. So let me kind of stop sharing here and I'll introduce the speaker. Here's stop share. Okay. It's really a pleasure to introduce today's speaker. Today's speaker is Professor Ning Lin from Princeton University. She is a professor of civil and environmental engineering at Princeton, whose research areas include natural hazards and risk analysis, wind engineering, coastal engineering, climate change impact and adaptation. A lot of her primary focus area right now focuses on hurricane risk analysis, where she integrates science, engineering, and policy to study hurricane-related weather events, how they change with the changing climate, and how they impact society, and how that impact can be mitigated. She's received a number of awards. So she's the recipient of a career award from NSF, the Natural Hazards Early Career Award, and Global Environmental Change Early Career Award from AGU, as well as the Huber Research Prize for from the American Meteorological Society. I mixed this up. Huber Research Prize from the American Society of Civil Engineers and the Walter Orr Roberts Lectureship by the American Meteorological Society. She received her PhD in Civil and Environmental Engineering from Princeton in 2010. And before joining Princeton in 2012 as an assistant professor, she conducted research at MIT as a NOAA Climate and Global Change postdoctoral fellow. So I'll go ahead and hand it over to Ning. So go ahead and share your slides, and you can go ahead and get started.
Okay, thank you, Arina. Thank you very much for having me. Hello, everyone. So today, I'm going to talk about my research related to tropical cyclone hazards and risk in a changing climate. So here's just a quick picture about tropical cyclones. This is a track of tropical cyclones over, I think this is over 20 year time period over the world. So when tropical cyclones become strong, they have different names. They are called hurricanes in North Atlantic. They are called typhoons in West Pacific. They may be called severe tropical cyclones, severe cyclonic storms, but they are basically similar storms physically. So in terms of the names, I may call them tropical cyclones or TCs or hurricanes, but what I mean is this kind of storms, basically tropical cyclones, but sometimes we just call them hurricanes for short. So when these storms make landfall, they can induce extreme wind, different categories that we usually talk about, but they also induce extreme rainfall, storm surge and waves, and this storm surge and waves will be go on top of astronomical tides and potential sea level rise and cause damage to coastal infrastructure and systems. here's some statistics about global tropical cyclone impacts over the past 50 years. There have been nearly 2,000 disasters associated with tropical cyclones. The economic damage was 1.4 trillion. Fatalities over almost 800,000. Over the past 20 years, the percentage of which the population of tropical cyclone-prone regions has been increased by 200%. So for United States, this figure shows a number of events from tropical cyclones and also the cost in billions. Two sides, and you can see that both numbers and the cost has been increasing over the past couple of decades. This year, we had two big events in Florida, Hurricane Helene and Milton, which would be at big spikes here too. So this recent increase largely because of population increase and coastal development, but they are also being affected by climate change. So tropical cyclone data is limited to really say how climate change has been affecting this damage, but some trends have been detected. So this study shows that proportion of major hurricanes has been increasing over the past decades. This paper shows tropical cyclones entering coastal regions to cause damage. So this is talking about the hazards, and then this is just some numbers about tropical cyclone impact around the world. As I mentioned, this figure shows that recent decades we have increase of tropical cyclone impacts and the numbers, and the 2004 would be a spike. So some effects of climate change has been detected, although the data is limited. So proportion of major hurricanes has been increasing over the past decades. This figure shows cyclones entering coastal regions where they cause damage has been increasing over the past decades. We also recently checked, what's about the time intervals between two sequential hurricanes impacting same locations or same states as we've seen in this year. And that time interval between storms has been decreasing over the past decades. So those are indicators of that climate change has been possibly has been changing storm characteristics, but with a lot of uncertainties given the limited data. Looking forward, we can use climate models to project how hurricanes will change in the future. So this is just showing histogram of models which predict percentage of change of intensity of storms. So most models actually predict that the hurricane intensity will increase in the future. But for the frequency, number of storms per year would have a different answer from different models. Most model actually shows that the frequency of storms will decrease in the future. But a few models, including very high resolution climate models and a model that we're using that I will show some results on, actually predicts that the frequency will increase in the future. So there's a big uncertainty about how hurricane frequency will change in the future. But if the intensity will increase, the frequency of most intense storms may increase in the future, which can cause more damage. So in order to understand how the hurricane hazards will change in the future under climate change and possibly urban development, and to develop mitigation strategies, we use this physics-based TC hazard risk assessment framework to guide our study in different components. So we start with global climate condition, which could be real analysis based on historical observation, could be GCM projections. So those GCM models generally have resolution about 1 kilometer. 100 kilometers or 1 degree. And so they actually have really low resolution in terms of resolving TCs, and they often miss intense TCs. In order to study tropical cyclones, we actually have to perform so-called downscaling or climatological simulation. So for such a simulation, we want to generate storms with characteristics including genesis, track, intensity, and size. And then given these parameters, we can apply hazards models to simulate the TC wind, storm surge, and rainfall. And the most of interest right now is about the compound hazards from TCs, and also other compounding hazards, including extratropical cyclones, sea level rise, and heat waves that are of interest right now. And also about the hazards information. On the other hand, we also study the exposure vulnerability of natural and built environment. And then combining hazards and vulnerability information, we quantify the risk, which could be characterized by, say, probability of failure, present value of future losses, population affected. Those can be used to support risk management or climate adaptation. We have looked at building code. How do we incorporate climate change impacts on building code? How do we mitigate design mitigation strategies along the coastline based on cost-benefit analysis and life cycle analysis and adaptation pathways? How do we apply this to insurance policy and also understand people's perception? So today I'm going to talk about a few components of this framework. So first, I want to talk about the climatology model, which is kind of the step of this chain of study to quantify the risk and the risk mitigation strategies. So the goal is to be able to simulate tropical cyclones on the future climate, and with the hope that with large numbers of samples, if we want to assess the risk and extremes. So some main methods, we can use global circulation model, GCMs. But as I mentioned, general GCMs cannot resolve TCs, but there's some very high resolution ones with resolution about 28 kilometers. They can explicitly capture this category 4 and 5 storms. But they're quite expensive to run, and sometimes they still cannot capture the full distribution of intensity. Second approach is dynamic downscaling. This is used by GFDL, is when they detect the storms in those GCMs, they use regional dynamic models to downscale each storm to get very high resolution estimation of the storm characteristics. But again, this is computationally even more expensive to downscale each individual storm. The method we use in risk analysis is often called synthetic downscaling, which is we would generate very large numbers of so-called synthetic storms given the low resolution GCM projection of the storm environment. And so that will help us to efficiently generate various storms characterized by track, intensity, and size to perform risk analysis. So this would be the method I'm talking about now. So there are a few methods specifically. One method by Carrie Emanuel in 2008 is called a statistical deterministic method that I used in many of the study that I'll talk about also. There's some other studies, and also in Princeton, we developed a model. So I want to talk about the model we developed at Princeton. But basically, the goal is to simulate synthetic storms under the larger scale climate condition. So the model we have is called a Princeton Environment Dependent Probabilistic Tropical Cyclone Model, or PEPC for short. So the idea is we should identify climate environment that's relevant to tropical cyclones, and then establish a relationship or statistical relationship between this environment, which is characterized by a few parameters, and the storm characteristics, including genesis, track, maximum wind intensity, and hopefully the outer radius of the storm. But this is still not well understood, the physics behind that. And then given the wind speed and outer radius, we can capture the radius maximum wind using a physical wind profile. And then with the maximum wind and radius maximum wind, we can calculate the pressure deficit. So those are the parameters that characterize a storm. And then with GCM, simulated future climate condition, and then we can use this model to simulate the storms very efficiently and consistently. So first, for the genesis, we model TC genesis as a dependent spatial temporal Poisson process. Basically, for the number of storms, initial storm counts in each grade, which I will define in a moment. Each grid and in each month is modeled as a Poisson distribution with a Poisson parameter depending on the environmental condition parameters that's relevant to just TC genesis, including vorticity, saturation deficit, potential intensity, and wind shear. Those will be obtained from the global climate model simulation. And then the model we developed, which is different from previous, is that we perform this regression rather than on regular grid on the ocean, we perform them on the clustering grids based on the similarity of environmental variables. So the idea is if you use regular grid and you have a low resolution, you would be smoothing out the variation within the grid. If you use very high resolution, because tropical cyclones still rare events, in many of the grids you have zero occurrence, and which will affect the statistical fitting. So we would cluster these grids based on these environmental variables to overcome this challenge. For example, for a particular month in North Atlantic, the algorithm will cluster this ocean grids into this 17 grids. And each grid has a similar climate condition for TC formation. And we perform the Poisson regression on these 17 grids. And then once we have developed the model, we can do the simulation also on clustering grids. And then within the grid, the counts will be uniformly distributed within the grid and the month based on the Poisson theory. So the simulations match with observation relatively well. Say here we're showing the comparison of the annual rate for the entire Atlantic basin. In black is simulation, the red is observation. So you can see we can capture the variation over time for the whole basin. Also, we can capture the seasonal variation here, showing distribution over the months of a year. So the peak is September. Simulation and observation match really well. And here we're comparing the spatial variation. On top is a simulation and the bottom is observation. We have some underestimation on the storm genesis in the main development region, but generally it captures a pattern and is improved over the previous model if we do not apply the clustering regression method. And then once we generate these storms, we can move them along, which is a storm track. So we have an analog wind TC track model. So the idea is that generally TCs are moved by the large scale environmental wind, but this large scale environmental wind has large uncertainties in our observation and prediction. So in addition to this environmental wind, we would add pattern we learned from the historical tracks. So we use 20 analog predictors based on similarities of the current track and the observed historical tracks, and plus environmental wind parameters that drive the wind. So we apply random forest model to train the model, and R square can get to 0.9 for longitude and 0.88 for latitude. So if we don't add a pattern, just the wind, the R square would be about 0.6 to 0.7. So here we're showing the comparison of the top is the observed tracks selected for Atlantic Basin, and the bottom is randomly selected tracks from our simulation. So you can see that we can capture the pattern of the track, including the recurvature in the high latitude. So we're showing the track density between observation and the simulation. Again, the pattern is really well captured. For the intensity, we have this Markov environment-dependent hurricane intensity model. So the idea is that intensity is related to a few parameters, including intensity. We're modeling intensity change, say 6-hour intensity change along the track. And then that would depend on, say, current intensity of the storm, last step intensity change, and also the environmental conditions, potential intensity, wind shear, relative humidity, and ocean cooling parameter. So, I mean, the first try is we could develop a linear regression between intensity change and these parameters. But we found that through some clustering analysis that actually storm intensity change is different somehow. So by just pure statistical clustering, we ended up with 3 groups of this intensity change. The first group is nearly 0 change, we call static group. And then second group is very large change on both directions, large increase or large decrease, we call extreme group. And then there's a green in between, that's we call normal. So that just indicates that we can use a homogeneous model to model all of them. So we developed this Markov model. Well, the storm intensity change will be moving from one state to another state as a Markov chain. And for each state, we model how the intensity will change. So the initial state probability looks like that. And then we have state transition, which is probability of moving from one state to another state. And then given the state the storm is in, then we have a intensity change as a function of this parameters. So all these probabilities depending on this x means all these parameters. So for example, when the x are at their medium values, this would be the Markov chain indicating the likelihood or probability of the storm being in each of the state or move to each of the state. And then in each state, we would have this intensity distribution. So state 1 would have very small intensity change, but the state 3 can possibly have very large intensity change. So we evaluate this model. So here we're showing the comparison of the between historical observation on the left and simulation on the right on the intensity evolution over the historical tracks. So you can see that we can capture the pattern very well. And also importantly, here we're showing the distribution of the so-called lifetime intensity of the storm. So the black is observation, red is simulations. And we grouped the storms into 2 groups. One group is those kind of normal storms. The other group is so-called rapid intensification storms. Those are the ones that happened recently also. So those storms are here. So the model can capture the intensity distribution for both storms compared to previous models, which cannot capture well this second group, because if you don't differentiate those extreme intensity change, this group will be mixed within the first group. And then we look at the model performance over the overall model performance at landfall. Here we divide the coastline into 3 sections and then look at the landfall intensity as a function of return period for each of the section and for all the coastline. So the black is 36-year observation. Red is 66-year simulations. They compare very well, but we can simulate as long as we want. Here the blue is 36,000-year simulations. So we can look at extremes that's beyond the historical record. And then recently we have used this model to downscale the global climate model CIMA-6. This is example for the high emission scenario. So this is so we simulate thousands to tens of storms for the Atlantic basin, and then we look at average storm frequency over the basin for each of these different climate models. And then black is the ensemble mean of these climate models. As you can see that our model predicts that the frequency will slightly decrease due to climate change over the century. However, this model also shows that intensity will increase. This is a distribution of the lifetime maximum intensity over time. So this curve is a mode. This is a mean, and the red one is a 90 percentile. So you can see over time, this distribution will be moving towards higher values, indicating intensity will increase. There's some details about also storms tend to move closer to the coast and northward that I didn't show here. But overall, there's decreasing frequency, but doesn't mean we have decrease of the impact. So that's about the TC climatology model. And given these parameters of the storms generated, we can simulate the hazards. So for the wind, we can use a simple parametric model that we call complete wind profile. So this is actually a merge of previous two models. This is the inner model, physical models. So this is the inner model describing the inner physics of the storm, but it cannot capture the outer region. So the solid lines are the observations for different categories, and dashed lines are simulation for models for the different categories. And there's another model called the outer models that describes the outer physics, but then it's missing the inner side. So we have this numerical merge, these two models to this complete wind model that captures both within the maximum wind region and outside. So this would describe the symmetrical wind distribution as a function of the distance from the storm center. And this model also can help us to estimate radius maximum wind given the out radius, because often radius maximum wind data is missing. So we have evaluated this model, and we show that the wind fields of tropical cyclone can more or less captured by this simple complete wind profile plus the simple background wind model. The background is just showing that the background wind is about 0.6 times the translation speed with a rotation. So here showing some evaluation. So this is for Hurricane Sandy. Our model is we call CIE 15. That's green, compares quite well with observation, which is H wind, the blue. The popularly used H80, so that's a Holland model developed in the 80s, quietly using hazards and risk analysis, is not that good in this case. And here we are showing that if we combine this wind profile with a simple background function that I just mentioned, this is wind field we get from Hurricane Sandy. And on the left, this is a H wind observation. So we can capture the pattern, asymmetric pattern, quite relatively well. In comparison, if we use H80 model, Holland model, with our background wind, the pattern is not that good compared to observation. So this model is very simple. It's not boundary layer simulation or anything. It's just a simple profile plus a background function, but can capture the wind relatively well. Here's some other valuation. So we can use the TC model, simulate a lot of storms, and then each storm will simulate the wind. And for any given location, we can figure out what is the maximum wind, 3-second gust wind as a function of return period. And then this is for New Orleans, GFK. The green dots are actually observation, and the blacks is a simulation. You can see that we can match with the distribution really well. So that's a evaluation of the TC model and also the wind model. And so once we trust the model, we can say estimate what is a 50-year wind or 100-year wind or 1,000, 3,000-year wind. We've done this. Just give you an example. Here's a 50-year wind at each county, coastal county that can be affected by tropical cyclones. And then here is a 50-year wind speed increase by 2050 on the high emission scenario from the baseline. So the application of this study was to evaluate how to develop a method to incorporate this information to building code of design wind maps. I'm not talking about here, but we actually checked that if we ignore this climate change in many locations, we design for risk category 4 level, which is high importance level. We actually designing for risk category 2, meaning we're underestimating the risk. So that's the application for building code. And that's wind. And for the storm surge, we use ASTIC model, which is developed by several universities, Notre Dame, UT Austin, and North Carolina. And because this model can help us to have efficient simulations with very high resolution along the coastline that we need to focus on, but a low resolution in the deep ocean to cover large areas that we need to focus on. So here is a mesh we have for the entire Atlantic basin with resolution about 1 kilometer along the coastline, but 50 kilometers in the deep ocean. But if we want to have a focus on particular region, we can zoom in this particular region. For example, of a study, we need to develop designs for Jamaica Bay. We can develop another mesh with resolution up to 30 meters. And then we use this low resolution model to screen over thousands of storms that we have for the Atlantic Basin and select the ones that actually can cause impact, and then use a high resolution model to actually study the impact and wave effect and so on. It's just a comparison of model storm tide and the measured storm tide in different locations based on this 1 kilometer mesh. You can see that the match with the historical storms are really well. And here's some comparison using this high resolution model for the New York region compared with historical storms. That's really well comparison. And we always try to balance the computational efficiency and accuracy, because again, we need to use this to do thousands of simulations. So one application here is we have developed flood maps or flood hazard projection for coastal regions. This is a 100-year flood level for each of the coastal county along the eastern U.S. Gulf Coast. Basically, we use the synthetic model, simulated up storms, and each of them go through the ASIC model. And then we do statistical analysis on the simulated storm surge for each coastal county and quantify what is a 100-year flood level. And we do that for the future climate projection. This shows what is the changes in the 100-year flood level at each location. And you can see that is a large change depending on the location. So this large change includes not only the storm characteristics changing, but also sea level rise. So here we're showing what is the relative contribution between the two at each county. So blue is a contribution from sea level rise. So at high latitudes, sea level rise is dominant factor in terms of the change of the flood hazards. But when we go to lower latitude, especially Gulf of Mexico, actually the storm climatology change can be comparable to sea level rise. So many studies studying climate change effects on coastal flooding focus on sea level rise, but we want to see that we would have to consider both, especially for low latitude regions. And recently we're exploring, machine learning approach. Although we have been trying to make ASIC simulations to be efficient computationally to deal with thousands of storms, but still it takes a lot of time. So here we use the neural network training on the ASIC simulation to predict storm surge at each coastal location as a function of just a few parameters of the storm near landfall. And then this is a comparison of the results between the neural network prediction on the X and the ASIC simulation on the Y. So it's really a good comparison, and it could be even improved if we make the machine learning model even more sophisticated. But this is just the initial try, and to say how much computational gains we will have, would that be helpful for us to scale up to the global level, or even more efficient when we go through many climate models scenarios. That was a storm surge. On the rainfall side, we use a simple physics-based rainfall model, and that model is basically just these lines of equations. There's no even solving equations. It's just the rain rate depends on the up motion of the air, and up motion velocity depends on the frictional effects, topographic effects. stretching effects, aberoclinic effects related to wind shear, and the constant of radioactive cooling effects. And just this codes run about a minute on the typical PC. And then here we compare it with a simulation from weather research and forecasting model, which I used 64 CPU for an hour for each storm. So on the left is WRF simulation for 2 storms of rainfall, total rainfall, and on the right is this simple model for this 2 rainfall. So 2 storms. So you can see that we can capture these patterns really well. And we also compare the model with observation. Here's one particular storm. That's a good one, actually. They're not always as good. This good one is Isaac, 2012. On the left is the simulation. On the right is reader observation. And we looked at some statistic annual average rainfall over 20 years along the coastline. You can see that we can capture the large scale patterns. And then zoom into Louisiana between the radar observation. This is a satellite observation, and this is a model simulation for the rainfall over some time period. So that's a really good comparison. But as I mentioned, first this model is good to capture the basic features and very efficient. We can use that for risk analysis. But still, this is a good case. It's not always very good because it's a simple model, does not capture rain bank effects or extratropical transitions or the other effects when storms deteriorating, not holding the structure. The model may not be that good. So we're also exploring machine learning here to see if we can leverage that. So here we used WRF simulation to simulate, I believe, nearly 30 storms. And uses images of rainfall to train the model. We also use satellite observation of the total rainfall amount, and then combine the 2 data set to train the machine learning model. Here on the right column, it's a WRF simulation of the individual storms. And the 3 left columns are showing the different quantiles of the machine learning simulation. And you can see that for many of the storms, we can capture, the machine learning model can capture the simulation quite well, even some kind of complex rain bands and features during extratropical transition. The storm that we cannot capture well is this Hurricane Sandy, which has a very different shape compared to others, and the model seems struggling with that. But overall, here's a comparison of the prediction of the rainfall, total rainfall compared to satellite observation for different quantiles, and comparison is really good. So just a direction to explore, to say the next step is to see if we can combine the physics model, that simple one, captures the main structure, and this machine learning model that captures the detailed features that a physics model did not capture. That's where we are heading right now. And mostly recently, we're very interested in joint hazards, especially here we're thinking about compound flooding with a storm surge coming from the coast, and then you have rainfall, riverine flow from the inland, and then causing a higher compound flooding than the individual flood drivers. This being discussed for some time, and here it is just showing the distribution, and those points here actually are TCs dominating the high end of the correlation between precipitation and storm surge in New York City. And this correlation has been increasing over the past decades. So that's kind of motivation for study. So we, again, use a synthetic model, simulate a lot of storms. Everyone goes through the storm surge modeling, rainfall modeling, and then we can look at the joint probabilities of this too. And here we're showing the joint return period, or related to, probability of exceeding 100-year rainfall and 100-year storm surge at the same location. So this probability is very low, so the return period is very long for high latitude. So meaning they are not that correlated. But if we consider the climate change emission with high emission scenario by the end of the century plus sea level rise, so the risk will be greatly increased. You can see the different scale here. So specifically for Gulf of Mexico, this kind of events will happen 20 to 200 to 400 years. At the historical climate will be 10 to 30 years in the future climate. And Mid-Atlantic, 300 to 600 years, will change to 5 to 15 years. To New England, which is very unlikely with 1,000 year return level at the current or historical condition, will become 5-year events. So this is a big change, and I want to also see this is we use a Emmanuel model which predicts its frequency will increase. So that's a dramatic change due to storm increasing, the frequency change and storm intensity change. Specifically here we show contributing factors for different locations from different factors. So the blue bar is a total climatology change, including storm surge change, rainfall change, frequency change, and their dependence between the two hazards changes. Sea level rise is green. So you can see that when we look at this joint rainfall surge hazards metric, the total storm climatology change is actually higher than the effects of sea level rise because of large driver of the rainfall increase in the future climate. Once we can model jointly the rainfall and the storm surge, we can model the compound flooding. But compound flooding at this moment is computationally demanding. So we're focusing on a specific watershed. This is in North Carolina. And so we use storm surge simulation from ASIC as boundary condition from the ocean. We use a hydrologic model for the riverine flow and a 2D inundation model, Hagrass models, to model the compound flooding. So here's a comparison with observation for historical storms on the compound flood depth. Once the model is evaluated, again, we drive it with thousands of synthetic storms, and then we can quantify what is 100-year flood depth for this region, and then what is 100-year flood depth by the end of the century for this region based on climate model simulations. So the challenge here is mainly the computationally difficult. We use some sampling method here, but still quite computationally intensive. So recently, we have developed a subgrid modeling for compound flooding in coastal systems, essentially incorporating a previous subgrid modeling developed in Notre Dame for compound flooding. So as example here, on the left is this simulation based on this subgrid modeling. On the right is a simulation at the same resolution, but no subgrid modeling. So you can see the difference. Essentially, it's making use of the information, terrain information at high resolution, but use a low resolution simulation. So we're saying this as a way to explore if we can speed up the simulation and do compound flooding simulation at larger scale. This is just another comparison to say if we use low resolution without a subgrid, we may model this kind of strange water level compared to observation, very far from observation compared to subgrid modeling. So we're hoping to see if we can use this to scale up the compound flooding at larger scales. So that's about the hazards modeling. Now I want to talk about the risk and risk management. I don't know if I have too much time. I will just quickly to scheme this. Now we have a simulation of storm, and then we can simulate individual hazards. And so we want to estimate losses from the tropical cyclones, considering these hazards. So previously losses are modeled as a function just the storm intensity, for example, or size. But here we want to model losses as a function of the hazards, rainfall, surge, wind, because we can simulate them and they are more direct causing the hazards. So this is a model based on the local hazards compared with the data, aggregated data for inch storms. And then once we have this model, we can say what it would be impact of climate change, changing the storm climatology. So this is a percentage of increase of annual expected annual damage by the end of the century due to storm intensity change, but no frequency change. And then this we can check what will be the contribution of socioeconomic change in this model, and then what will be the combined change. So this it's just a work to link our simulation to economic loss estimation. Second application we want to talk about is power grid. So we know that 9 out of 10 biggest power damage in recent history in the United States are due to tropical cyclones. So we developed a power system modeling method where we consider the energy generation, including renewable energy, and then we have the transmission network and distribution system to get the distribution of the power and to the customer level. And then apply this model to Puerto Rico. Puerto Rico experienced 2 events, Hurricane Maria 2017 and Fiona 2022, which caused 100% damage in the Puerto Rico island. So here is just showing the time history of the power loss in this island. From here to here, just 10 minutes, the drop is 50% loss of the power within 10 minutes. So this is called a cascading blackout. So here, the black is this observed time history of the percentage of customers with electricity. So this is a drop in 10 minutes from 50 to 0. And then the other, the green curves is our simulation, Monte Carlo simulations, mimicking this kind of event using our model. So you can see that we can capture this cascading failure. We can also use this model to say, with renewable integration, the renewable integration, because renewable energy relies on the environment, so they are not stable and they can cause instability in the grid. With large integration, we may have higher risk in the grid. So we're here showing using this model to test if we put renewable penetration at different levels, when are we going to see a big impact? So we can see that if the renewable penetration is greater than, say, 45% in this island, we will be seeing a large increase of the risk. And they do have a goal of 100% renewable by 2050. So this is kind of an image they need to consider and put a storage and other solutions to prevent the risk. Another interesting direction we want to connect is related to heat wave. Recently, we've been seeing some events in New Orleans that and also in Texas this year, well, the heat waves following the hurricanes. When hurricanes cause damage to the power system, we lost air conditioning and the refrigerator, everything, and then we get heat waves. So we want to model this kind of combined compound hazards. So on the one hand, we can use global climate projection to simulate the hurricane, the hazards, and take out the heat wave or heat stress, including relative humidity. On the other hand, we can model the power damage based on the vulnerability model, and then power system model. We also model restoration based on the priority guidelines of restoring priorities, restoring the damaged system components, and then we can quantify, say, what is the likelihood of getting this heat wave without power for some time for residents in a particular location. So we applied it first to Houston, but here we showed it for Louisiana. So here we're showing the percentage of customers with power as a function of days after hurricane landfall. This is Ida, this is Laura. So you can see that observed, which is blue, compares well with our simulation, which is red. And this is just showing the distribution in Louisiana compared with observation. And then we can, again, couple that with our thousands of synthetic storms on different climate conditions. And then here we can show what is the interruption hour by power outage as a function of return period, or interruption hour by compound hazards, meaning no power but heat wave as a function of return period. And here the dashed line shows the level for Hurricane Ida. So for Hurricane Ida, for the compound hazards, it's about this picture shows better. So the compound hazards in the historical state would be 278 years event, which is 30 million customer hours of compound hazards. But by the end of the century, it will become 8-year event. And here we break down what are the contributors here. Contribution from sea level rise is not very high because we're talking about a whole state. Sea level rise is more on the coastal. And then hurricane intensity change will contribute this much. And the temperature increase is, of course, the largest contributor. And then they added up to a big increase of the risk. So this is just showing that uncertainty of our frequency, if we assume our frequency prediction is uncertain, would that change our results much? It's not changing our results much because it's mainly driven by temperature increase and also intensity of the hurricanes. Finally, I want to talk about adaptive strategy for the coastal region. As example of Hurricane Sandy, people are talking about how to protect Manhattan. And then, so here's a design called Big U, which is a wall of 16 feet based on 100-year flood level plus 1% quantile of sea level rise for 2050. So we think, and this kind of design logic is being used in many places. We think we can improve this kind of design by considering cost and benefit. We should consider that climate change effect is increasing over time. It's not static. And also climate projection is deeply uncertain. Uncertainty is larger and larger as time goes on. As our projection time horizon is longer. But we know that we can systematically learn and adapt. We'll not just make a decision and let it be, right? We can adapt. So based on that, we can think about a strategy by minimizing the total cost due to damage and the investment discounted to now. Okay? But the strategy can be changing over time. So say for levee, it can be increasing over time rather than a static one. So what would be that time path of the levee in the optimization? So different method can be applied. The key is how do we consider the uncertainty of the storm surge distribution and the sea level rise distribution, right? So one thing we can do is use dynamic programming. So we can design a levee going up over time, but we're using the projection of the climate as now. So we see that large uncertainty will have, say, to the end of the century. Secondly, Bayesian learning. We can check the sea level rise every, say, 10 years, and then redo the projection of the climate, change our plan, and so that we can kind of confine this uncertainty over time. Better, we can use reinforcement learning, which means that at any given time when we make a decision, we're not only just using the observed sea level rise up to now and learn what's going to be future, but we're also taking into account that in the future, we're going to learn, we are going to observe, and we're going to learn, we are going to adapt according to the future simulations, future conditions. So with that, we can actually be less conservative as we make our current decision. So here's results. So here we're showing in the middle is the sea level rise projection over the century. On the right is storm tide projection. Different color shows different decades. So the storm tide will be increasing over the century. And on the left is the strategies that we derived. So the big U is a constant line over time, which is green. And then we can do cost benefit with static optimization, which is a black line. And then the blue curve going up is dynamic programming. And the shaded red is reinforcement learning because it's a probability distribution depending on the future observed sea level rise. So we look at the total expected cost for different strategies on the different emission scenarios. The top line is mid emission scenario. The low line is a high emission scenario. And so we can see that reinforcement learning is much cheaper compared to other method, especially this PQ and especially on the high emission scenario case. So this is an idea that they have been discussing about flexible adaptation and so on. But here we found a very effective machine learning tool to fund optimization of such flexible adaptation strategies. I think I don't have too much time, so I will stop there and hopefully there are a few minutes for questions. Thank you.
Thanks, Ning. Excellent talk. So I would tell everyone to clap, but we're virtual. Are there any questions for Ning?
I have a question. Ning,
Yes.
where's your data? Can we get access to your wind and rainfall data for some of the storms, future storms that you've?
Rainfall data. So we have so depending on we have papers on rainfall that data will be available. But we also have a new projection that I showed for the CIMA 6. So we have a CIMA 5's rainfall data that's available. And we have CIMA 6 storms available, but we haven't generated rainfall for CIMA 6 downscaling.
Okay.
If that's needed, that we can just
I'll reach out to you off.
Yeah, let me know what you actually need.
Thanks.
Yep.
Other
Very
questions?
nice talk, by the way. That was great.
Thank you.
So yeah, I have well, I can ask a few questions, but I'll just start with one. So at the beginning, you were talking about sort of like the scales of climate models, of global climate models being too big. I was just curious if you're familiar with some of the up and coming very high resolution atmosphere models. There's a SCREAM model that can run at a 3-kilometer resolution using GPUs and things like this. I was just curious if you think that some of these models could potentially help with some of your work, or if you guys have started kind of looking at maybe using some of them.
Yeah, I mean, I don't know exactly the 3-kilometer models, so but that would be great if the computational effects can be overcome. So right now we are, because say for design we're talking about 3,000-year event, so we need to simulate 3,000-year storms. So the question is, can this kind of models can be with reasonable computational effort to generate?
Yeah, I think that's a really valid point, because initially when you started, I was thinking that's like if you're looking at a particular year, right, and you want to predict hurricanes in that year, that's a relatively short time event. But then if you're trying to look at hurricane frequency over like hundreds of years, you would need a lot more. Yeah, and I think you're right that these finer resolution models currently, I think the time integration is always going to be a bottleneck.
But I think that could be, I mean, one way is to think about the combination of them, right? Right now we're training a model or using a model to downscale very low resolution GCM. But if we use that to downscale relatively higher resolution models, that probably make it more accurate and more still efficient, things like that.
Yeah, you could do like some kind of multi-fidelity type of an approach. Let's see, does anyone else? Lindsay, your camera went on. Do you have a question?
Yeah, I had a maybe naive question. How does what you've been doing compare? Or I noticed you mentioned the number of like GCMs that can capture storms, and how does some of those or what you're doing compare to the high-res MIP multi-model ensemble that has produced tropical cyclone frequency and intensity information? I know that that particular one tends to underestimate intensity, I think, but I would just be curious how it compares. I'm still learning in this space and what data there is.
Yeah, I think the intensity prediction pretty consistent among different models and different approaches in terms of intensity distribution, if the GCM can capture the intensity distribution, and then they also tend to give higher intensity. We actually, put it this way, we actually did a comparison specifically using our model and Emmanuel's model, and to downscale GCM, high flow GCM, which can produce intense storms. But in that particular GCM, it's actually a little bit more intense. So that GCM tends to have very large intensification, a little bit than we expected. So at this point, it's not totally sure if it's which one is better, because we don't know what the future will be. But in general, we just feel that particular model can be a little bit more intense than other models. So
Which
that
one?
there are some uncertainty in terms of magnitude of intensity change between models. But in general, I feel like the big picture is they are showing some kind of increase of intensity. But the frequency can be quite different, right? So some of this high resolution GCM actually predict frequency will slightly increase or similarly constant, similar to historical slight increase. Manu's models that I showed is in our applications actually shows frequency will significantly increase. And in our model, statistical model, there's a key parameter called the saturation deficit representing the relative humidity. If we use that parameter, the frequency will decrease as I showed. But if people use another parameter called relative humidity, actually its frequency will increase. So there's uncertainty there. We don't know. So in our adaptation analysis, we often check the uncertain sensitivity to the frequency projection.
Okay. Then I just had one last question. Have you looked at all into, or do you have a sense for how the length of the season or the start or end of the seasons of the hurricane season is changing from the work that you've done?
Interesting. Yeah, we actually submitted a paper, revising a paper on that, because what we're interested in the compounding of TC and heat wave, right? So if the seasoning is increasing, then they're not more likely to compound as it. So we actually found in our simulation, especially for GCM at GFDL, the TC season is actually going to be length. So it could be the peak will be shifted to later of the season. There's a Nature paper actually said it will shift to front, but there was another paper said it's shifted later, and we agree with the second paper. So that's something on the investigation. Yeah, so there are just a couple papers available on that topic.
Okay, thank you very much. It was really excellent.
Great, thank you.
Any other questions? So I was just gonna ask one thing related to Lindsay's first question. So I'm not an expert on this, but I was kind of surprised that the frequency is actually expected to go down in a lot of the models. So you showed results, I think, for the highest RCP scenario, but have you looked at like the lower RCP scenarios to show that? Like, I'm just wondering, is it like, does it proportionally go down, or like what are the physical? Do you have any physical intuition for why the frequency would go down?
First, we looked at other emission scenarios going down. But we haven't really found very consistency yet. I could check because say we will look at 14 GCMs. I didn't say, all GCM shows 4.5 goes down more than 8.5 or the other way. I haven't found that kind of trend. But generally, they go down. So the key here is that in this statistical model is this parameter called related to the relative humidity. Humidity. So that parameter is being known that it's going to be changing this direction. Yeah. So and that parameter is known to be more physically reasonable as a parameter. So and many of the previous models actually agree that frequency will go down. So at this point, it's more models says frequency will go down than models
Yeah.
frequency will go up.
Do you know like the physical reason for why I mean, I guess a warming climate would cause the frequency to go, there must be, well, if you don't know, it's maybe outside your, I was just curious, but I could try to look into this offline, but.
I mean, I know a little bit, but I don't think there's a clear answer from anyone.
Okay.
That's
Okay,
why
okay.
frequency is a big component. People talk about,
Yeah,
you know, the seeds, the possibility of starting, and then the possibility of from starting to become the storm. So
yeah.
the starting point, the physics of the starting point is also not totally clear. So
Right.
big
Okay.
on-
Well, if there are no more questions, let me see the chat here. Oh, is there something in the chat? Oh, there were just comments how people liked your presentation. Thank you very much for those who are still on. This will get posted on our webpage if you know people who'd like to see it who missed the talk live. The next webinar will be on December 17th by Professor Todd Griffith from University of Texas, Dallas on some wind modeling work. So I hope to see some of you there. Thank you.
Thank you. Thank you all. Bye.
Bye.